In our first example, we're going to introduce the idea of compound interest by actually using our simple interest formula from the previous section. Right, so we're told to use our simple interest future payoff formula to find the following. And that's going to kind of lead us eventually to the idea of compound interest. Remember this formula that we saw in the previous section? F equals P times 1 plus RT. Right, so what we're doing is we're taking our principal times 1 plus our rate times 10. Right, you deposit $100 into a 1-year certificate of deposit paying 10% compounded quarterly. Right, quarterly meaning 4 times per year. Determine the amount F to which the $100 deposit will grow in a year. Right, so if we start this like we did in the last section, right, I'm going to write our formula. F equals P times 1 plus RT. Our P is 100. Our R, our interest rate, 10%, 0.10. And our T, a quarter of a year, right, 1/4 of a year, that's going to give us 0.25 if we write that as a decimal. All right, so now we're going to plug this into our formula. F equals 100 times 1 plus 0.10 times 0.25. Right, we're going to plug this into a calculator. Again, we can plug it in using parentheses, or if we're doing it step by step, multiply, then add, and then multiply, kind of working inside to out. We get F is 102.50. Right, so after the first quarter, instead of having $100, it has now grown to 102.50. Right, now for our second quarter, we're still going to use that same formula. And that's also going to be true for our third quarter and our fourth quarter. So I'm going to go ahead and just keep writing this same formula right in here. Now what's going to be different, our rate and our time are still going to stay the same. Right? So we're still looking at a 10% rate, we're still looking at quarterly, so we're still going to use a time of 0.25. But what's going to change in each of these different quarters is our principal. So in this case, our new principal that we're going to use is our answer from part A, our 102.50. Right, so into our formula we go. 102.50 times 1 plus 0.10 times 0.25. We can put the 0.10 in parentheses as I did here. We can leave them off as we did in the previous example. It doesn't really matter as long as we have parentheses around the entire part outside. Right, that's just showing multiplication. This is going to give us F equals 105.06. Right, now when we move to our third quarter, this is going to be our P, 105.06. So again, into our formula we go. 105.06 times 1 plus 0.10 times 0.25. This is going to give us 107.69. That's going to be our P going into our fourth quarter. 107.69. Alright, so again, into our formula we go. 107.69 times 1 plus 0.10, 0.25. F equals 110.38. So this is our final value here. Right? So what we've just done is we've actually just done a compound interest problem. But the difference is we just, instead of using our formula once for our compound interest formula that we're going to get, we just kept recalculating. And if we look at this, and if we kind of compare these, notice that in this first example, right, our interest Right? If we take our 102.50 minus our original investment of 100, well, that gives us $2.50 interest for that first quarter. Right, now if we subtract our next principals, so if we take our 105.06 minus 102.50, again, we're just going quarter to quarter. We're not going from our original. So 105.06 minus 102.50 is going to give us 256. Notice that our interest has increased by a little bit. Right? Our time hasn't increased, our interest rate hasn't increased, but what has increased is our principal. That means our interest is going to increase a little bit. If we take our 107.69 minus 105.06, 107.69 minus 105.06, we get 263 interest. And then if we take our final 110.38 minus 107.69, we get 269. Right, so our interest increases just a little bit each time from our original amount. And the reason is because we're finding interest on the interest that we've previously added. Right, so each time we add those extra, or add that extra interest into our principal, then we do our calculation again, and it continues to grow. And as we're thinking about and as we're using our compound interest formulas, we're definitely going to see a difference in how many times it's compounded per year, and different things. So compound interest can be a big factor as far as growing an initial investment can be. Right. This example at the bottom is going to be kind of connected to this previous example. So I'm going to go ahead and do this one kind of all together in this video. In this example, what we're looking at here is we're going to kind of generalize a formula for something along these lines. So we're still going to use our simple interest future payoff formula. So the same formula that we used in the last example. And we're going to set this up pretty much exactly the same as we did our previous example. The only difference is we're not actually going to go through and we're going to calculate this. We're going to kind of leave it in mathematical notation. So in this case, you deposit $1,000 into a bank account and your bank compounds the interest at an annual percentage rate, APR, of 5%. So our formula that we're using, F equals 1,000. Or excuse me, not 1,000, not in our general formula. That's what we're going to plug in. Let's write out our general formula though up here. P times 1 plus RT. All right, so I'm going to go for our first step. I'm going to go through and kind of color code these. So I'm going to start by plugging in 1,000 for P, as I just tried to do up there. 1 plus our interest rate is 5%. 0.05 times our time, which is 1. Right, well, multiplying 0.05 times 1 isn't going to change it. So I'm going to write what we're going to bring to our next period. I'm going to write it as 1,000 times 1 plus 0.05, excuse me. This is going to be our new principal that we're going to carry to our next period. Right, so into our next year. Right, so now we're going to do this again. Right, but we're going to take this new principal and that's what's going to go out front. So out front, instead of just having the number 1,000, I have 1,000 times 1 plus 0.05, because that's what I had right here. Now, I still need to include this part here from my previous formula, right? My 1 plus RT. So now I have 1 plus 0.05 times 1, which then if we simplify this, right, both of these turn out to be the same thing. And if we're multiplying two things that are exactly the same together, we generally use exponential notation and we show that it is something squared. So I'm going to keep the 1,000 out front and then we have 1 plus 0.05 squared. That is our new principal. All right, so now we're going to use this formula again. Our principal is what we have written here in green. 1,000 times 1 plus 0.05. Right. And now we're going to use our 1 plus RT, which is going to be to repeat the same thing that we've seen here. 1 plus 0.05 times 1. And I lost that green guy had a squared, so make sure we get a squared on that green guy there. All right, so now if we look what we have here, well, we have 2 of these guys right here. That's really the same. So now using exponential notation, we have 3 of those. So we have 1,000 times 1 plus 0.05 to the 3rd factor. That is now our new principal. Right? And if we think about this, what is increasing each time? Well, pretty much everything in our formula is staying the same. We're just increasing our exponent. We're multiplying the same thing by itself again and again. So we can generalize this for a time t. And write this as 1,000 times 1 plus 0.05 to the t power. However many years it's been is going to be that t. Now this is going to give us if we change all of our values back to variables, p times 1 plus r to the t. Right. Now this formula that we see at the bottom here is not our exact compound interest formula, but it's very, very, very close. So if we regeneralize what we started with, right, this is going to give us that. We're going to say which is close to our compound interest formula. All right, now as we've gone through these 2 examples on this page, it's taken a while, right? It's taken a while to go through these examples. So what we're going to do is, instead of recalculating the same thing over and over and repeating ourselves over and over and over again, we're going to use the idea of our exponential notation to assist us with our compound interest formula. And that's what we're going to see in our next video, and then we're going to do a bunch of different examples using our compound interest formula. So these first 2 previous examples, hopefully you're able to follow along, but for the most part, we're not going to do a lot of this. We're going to shorten this process drastically, which I think by now you would agree with me that that's going to be a good thing if we don't have to do all this multiplication over and over again, and we can shorten this process.